Okay, in this video, I'm going to show you how to do one of the more, or basically almost the most advanced thing I'm going to ask you guys to do in Mathematica. In MATLAB, we learned how to solve ordinary differential equations, both first and second order, using numeric algorithms like Euler's method or Runge-Kutta. You basically cannot solve first order or second order differential equations symbolically in MATLAB unless you use one of their fancy toolboxes. And most differential equations that we want to solve in the real world, like the ones that describe the flight of actual rockets or real systems, can't be solved analytically anyways. So those are very powerful techniques. But when we're taking physics classes or math classes, we're introduced to a plethora of differential equations that do have an analytical solution, or basically I can solve this second order differential equation and find an expression that is a mathematical expression. So we're going to go through an example here that should be familiar to the physics majors, and that's an object in free fall or a ball thrown straight up in the air, only feeling the force of gravity. So this is Newton's second law describing that type of physical system, right? F equals ma. In this case, the only force acting on it is the force of gravity downward. So ma equals negative mg. Cancel out the m's, and then I can rewrite acceleration as the second order derivative of a position with respect to time. In this case, I'm using z for my variable of position in the upward direction. This is a second order differential equation that I can solve. So I'm going to use dsolve. Dsolve is Mathematica's built-in solver for differential equations that have an analytical solution or have a symbolic solution. So it's going to basically spit back out, if it can solve for one, if it is an appropriate differential equation, a mathematical expression that solves or satisfies this differential equation. Okay, so the first thing I'm going to do, I'm going to use this simpler syntax, which I didn't know about when I made some of these notebooks, to clear all the variables. So this should clear, hopefully, all the variables in my notebook. I'm just going to double check. Maybe that did not clear all the variables. Nope. I guess not. So I'm going to go back to this one. Okay. I'm not sure why that's not working, but we're going to keep going with it. So clearing the notebook, and then what I'm doing here is I'm making, it's going to seem a little weird, the syntax, but that's kind of how Mathematica is. I'm basically setting up a system of equations for Mathematica to solve for my differential equation. And just so I don't give away the answer here, I'm going to delete the output. So like I said, this is a second order differential equation with respect to time. So this is how I would type that in to MATLAB or Mathematica if I wanted to take a second derivative. And what this is saying in this list basically is that I'm specifying that the second derivative of z with respect to time is equal to negative g. Okay, so it's just a way of typing out this here. And I'm storing it in this new variable equations, and it's a list. If I wanted to, I could just put something like this straight into dsolve, but this is just one way to do it. Okay. So what dsolve is going to do is it's taking a list of expressions. In this case, the list only has one item in it, but it could have more. I'll show you an example in a second where it has more. And it's solving the differential equation for an expression of z with respect to time. Okay, so this says, hey, I'm looking for the solution of this differential equation. I'm looking for a general solution. Give me a z of t with respect to time. So that's just the syntax there. And let's go ahead and run that. So what do I get out here? This first bit is just coming from here. That's just what equation's equal to. And then the output is a double nested list, which is not great, that contains a single replacement rule. So this arrow notation is called a replacement rule. And in this case, the reason why it gives it as a list is that for more sophisticated things I might ask dsolve to do, I might actually get output multiple things in a list. In this case, it's only outputting one thing because this differential equation only has one general solution. So for a differential equation, the general solution is what I get out if I haven't specified any initial conditions or boundary values. So that's why I have something here. This is the solution, but it's got some unknown constants in it, and that's what the C1 and C2 are. Okay, so if I want to actually use this equation in something else, I've got to do something called the replacement rule. And this, again, is the confusingness of Mathematica syntax. It's basically saying, let me just run this. And it's a way to extract what's inside this nested loop. I really just want, right, this expression maybe so I can plot it or do something like that. It might help if I kind of show you this one step at a time. So I'm going to go up here. And just to remind you, dsols is what was outputted. That's just what was outputted by the built-in function. What I'm doing here is I'm basically saying, like, replace z of t in this list with what's in dsols here. But because dsols is a double nested loop, the first time I do this, it's actually replacing it with something that still has brackets in it. So it's still just a single nested loop. So by adding in this list notation saying, hey, give me the first item in the double nested loop, I want that to replace this thing here in dsols, okay, then I can extract just the mathematical expression. It's crazy. You just kind of have to follow the examples. That's what I do. Or maybe if you do it enough times, you start to remember. But that's this kind of thing is why you see this slash dot notation all the time, because sometimes what comes out of this thing is maybe more than one expression. And in that case, you might want to pick a particular general solution. So this one only has one general solution, so I'm picking the first one, but maybe if I had more than one, I would put a different number in here to extract that general solution. Anyways, that's kind of sophisticated. Maybe you guys will get there. All right, so this is a general solution. It has some unknown constants. How can I do better? Well, again, the reason why I am specifying this variable equations or EQNS as a list is that I can actually specify more than one condition as I put it into dsol, or basically more than one mathematical relationship that is true. So not only is the second derivative of z with respect to time equal to negative g, I also know that z at t equals 0 is equal to something z naught, the initial position in the z direction, and the first derivative of z with respect to time, which is the velocity, I'm going to say that's equal to a different variable called v naught. Okay, so what we're going to see here when I evaluate the same differential equation is that, and then do the same things, and maybe I will get rid of this for a second, is that basically it can do something better, right? It can solve for what those constants are in terms of these variables that I defined in my initial conditions or my boundary values, okay? So again, this is just the outputting what this line is. This is outputting what the new solution is, okay? So now it's not really a general solution, although I haven't specified what those velocities are, but that's what's nice about doing symbolic math. So now it's giving me something that hopefully looks kind of familiar to you guys. It's a solution for the position in the vertical direction with respect to time. And then I'm just here extracting basically that mathematical expression outside of the double bracket. So I'll put this expand back in so we can see what that does. So basically, let me take it out one more time so we can compare. It's just basically writing it in a way, it's propagating this 1/2 through, so it's writing it in a way that's a little bit more familiar to us, okay? So this looks like just like the kinematic equation for something thrown straight in the air. So you guys learn this in first year physics. It is a solution to a second order differential equation, okay, that I can write from first principles using my knowledge of Newton's second law. All right, so let's take this a little bit further. Let's plot the solution. So if I want to actually make a plot of this, I need to tell the program what g and v naught and z naught are if I want to plot the position with respect to time, because it won't be able to calculate a value to put on the plot without numerical values for those constants. So that's what I'm doing here. So basically here, I am saying, let me put another cell in here so you can see this. And again, this is just crazy Mathematica syntax, but it's saying, okay, let's create a test case condition. Let me get rid of this here, where I'm going to take my expression, this one up here, and I'm going to substitute in or replace 9.8 with G, 9.8 for G, 0 for Z naught, and 100 for V naught. So that's what I'm saying. I'm saying take my position expression and then make all of these replacement rules. So go up here, that's the slash dot notation, and replace these variables with these numbers. And then this is just regular plots. Let me just show you what this does in a separate line. Oops. Okay, so you can see it's just made a new expression. So now that's what's in here once that runs, and then it just can make that plot. Okay, boom, looks just like what you guys could do without all this Mathematica. Okay, so the nice thing is that we can go back, right? We still have these general forms of the solution. So if I wanted to make more plots with different values of G and Z naught and V naught, I haven't really changed the way that I've done this calculation, what the general solution is for that differential equation. If I wanted to continue working with the solution, I can do that. Again, some of this is going to seem silly because I'm just kind of going back to where I started. But if I wanted to have an expression for the velocity, of course, I can take the first derivative with respect to time of the position. If I wanted to have an expression for the acceleration, I could take the second derivative with respect to time. And then if I wanted to make plots of those things, I can use the same replacement rule for this test case to plot those values over the same time range. So here I did from t equals 0 to 21. So let's do that for velocity and acceleration. Okay, so for this, it's an object in free fall. Initially, it's got a positive velocity in the positive z direction or upward direction. At the top of its flight, its velocity is instantaneously 0, and then it turns to a negative velocity as it comes back down. For an object like this in free fall, the acceleration is constant. So I get things just like I'd expect. And if I wanted to come back here, I can change my test case. So I can change the acceleration, for example, and run everything again. Pretty simply, I can go ahead and remake the plots. Okay, and the only difference that you're really going to notice here is that the acceleration is different. And then because we're on a planet with less gravity, or we've reduced the acceleration in 21 seconds, basically it doesn't get, it just barely reaches apogee and starts coming back down. Okay. All right. So cool stuff. Well, really powerful, and it's nice in Mathematica. Again, like the MATLAB notebooks, you can mix text and the physics to really explain your solution, your either numerical, in this case, symbolic math solution to a problem. Okay, the last little examples I'm giving here is just going a little bit further. So let's say I wanted to use these expressions that I just derived or just solved for using dsolve to solve for some other quantities. So here I'm using the built-in analytical solver, solve, which we learned about before, and I'm taking that position equation that I got out of dsolve by solving that second order differential equation. I'm going to substitute in that original test case. Let me actually rerun this so I make sure that that's what those are equal to. And I'm going to look for where the position is equal to 0. So basically what this is saying is find the time when the position is equal to 0. Okay, so let's go ahead and run that. So when I do that, again, I'm getting a couple of different answers. So solve is giving me a couple of different, in a list, answers for that satisfy what I've asked it to do. I said, hey, for this test case, tell me when t is equal to 0. Okay, and I can pick which solution makes the most sense to me. And in that case, it's this one here at 20 seconds. So how do I extract it from this list format? Again, I can use the replace rule. So I'm like saying, hey, go into this list and replace T with the second list item in solutions. So solutions got 2 list items. This is the crazy indexing notation that says take the second one and then make that replacement of T with it. So what I'm getting for return time is just a numerical value of 20.4 seconds. Okay. And then here, I'm taking it one step further. So remember, the velocity is another expression. The first thing I'm doing with that expression, with this first slash dot notation, is replacing the constants with my test case. So I'm replacing G and V naught with what I said in my test case. And then I'm doing another slash dot to say, hey, now replace T, do this replacement rule, replace T with 20.4 seconds. So this tells me that the velocity of my projectile when its position is equal to 0 is negative 100. Okay, so basically when this thing hits the ground here, it's going 100 meters per second. Okay. All right, let's do one more. Okay, so now I'm going to do the same thing, but I'm going to look for its peak altitude. So I'm going to solve this for when, with the same test case for when the velocity is equal to 0. Very similar syntax to what I did before. It finds the time is 10.2 seconds. That hopefully makes sense, about half the time it took to hit the ground. And then I can find the peak height, again, using that same kind of slash dot notation. Okay, in this case, there's only one solution when I call solve. And then, so I'm going to go ahead and take the first item in the list. Okay, so that was a long example, but that's how we can solve ODEs analytically using Mathematica.